Hi everyone, welcome to DeepRob lecture 12. Today we're gonna talk about object detection. So in a way, we are gonna move from the most basic block in computer vision, which is image classification, and look at some of the stuff that we care about in robot perception, such as objects, how do we detect them, and so forth. So today we'll talk about object detection. But before I get into the technical details, some administrative stuff. So project 3 is released. Instructions are available on the website. And again, we are going to use props dataset and specifically detection dataset. So in this particular project, you'll implement CNN for classification and then improve that to detection using faster RCNN. So it's due on March 14th. Considering the spring break, I think you have ample amount of time to do this project. I would highly encourage you to get started early on, because the next project you will probably have to finish up in faster than this one. So yeah, so this is exciting, right? You'll be looking at multiple objects in the scene. You want to be able to detect them, localize them with bounding box, and also tell what that particular bounding box is. Okay. Final project tasks. As I mentioned earlier in previous lectures, the first part of this is the project proposal submission. Again, my recommendation is that each member should have read papers in the topic and should have discussed with their team members, so that you can collectively make a decision on what paper you're going to implement, reproduce, and extend for the final project. So paper selection is due tomorrow. Again, I think the expected thing out here is that each team member should have read the paper that you are selecting. So make sure you read the paper and you understand what needs to be done, so that you can propose what elements of that is going to be reproducible and what is the effort among your team members. So I'm imposing the soft deadline, which is tomorrow. So please update your group row with the paper on the Google Sheet. And for next week, you'll have to submit the final project proposal. And I'll be sending out a template soon. And this is going to be just 2 pages. So I think once you decide which paper it is, it should be easier to write this up. So this is due next week. Any questions on this? Okay. The in-class student lecture presentations will start on 2nd of March, which is next Thursday. Like I said in the last lecture, if you are presenting on Tuesday, meet with me during my office hours on the previous Wednesday. And in this particular instance, the first presentation will be next Thursday. So that particular group will meet with me tomorrow during the office hours. So tomorrow's office hours will be both online and also in person. So I'll be in person in Shepherd 161 if you want to meet in person and discuss. I'm assuming that this discussion with the group will be for 45 minutes from the beginning of the office hours, so that I can give the other 45 minutes for students if they have any questions on projects, lectures, or final project. Any questions on this one?
So the lecture presentations are aimed to take up almost all of class time, pretty much?
Yes.
Okay.
Yeah, so the idea behind that is I want the team to actually prepare the background behind the paper or the topic they chose. So for instance, if it is RGBD, which is going to be next Thursday, so we'll cover the basics, like why do we care about RGBD? What are the sensors that are out there? And what is the data format? And then we'll start looking at a little bit of methods that have been used before using deep learning, and how the deep learning architectures that we talked about have been extended for RGBD data. And then that particular group will actually talk about one instance, which is the paper that they chose to implement, and they will go in detail on that. So I think this will happen for every topic and every paper, so that the entire class will get not only that particular paper, but also like a good idea about the topic, so that they are aware of some terminologies and hardware and tools to use. Okay, if there are no questions, I'll move on. So in the previous lecture, we talked about deep learning software, and specifically we talked about PyTorch and the computational graphs, static versus dynamic features, and so forth. And in general, overall in the lectures, we've been talking about image classification. So given an image, you have this neural network, for instance, AlexNet in this case, which kind of generates a feature at the end of the layers, and then the final fully connected layer converts that input tensor, which is 4096, to 10 values, which are the number of classes in your classification problem. So in this specific case, if there are 10 labels of different food items, we are classifying this image to be containing chocolate pretzels. So, but there are other computer vision tasks that are very fundamental and also very popular. You might hear this if you're looking at the literature. So one is, the first one is classification that we already saw. Second one is image segmentation. So here you are not talking about objects, but you're talking about pixels. So you're basically classifying each pixel in your image to be one of the classes in your labels. For instance, if there are two labels here, chocolate pretzels and shells, each pixel is being classified into one of these labels. The other computer vision task that is quite popular, especially in the context of robotics, is the object detection. So here you have multiple objects, and the idea is to be able to draw the bounding box, which is to localize where a particular notion of object is. For instance, there are 3 different objects here, so 3 different bounding boxes. And then for each of these bounding box, you want to have a label that is associated that says, okay, this particular bounding box is one of the kind of the pretzels. The other computer vision task that is also popular is instance segmentation. So it's not only about segmenting each pixel to a category and a background, or let's say on a category level, let's say food versus non-food items, or in the sense of autonomous navigation, it could be like, okay, that's a vehicle versus a road versus, let's say, people. But then you want to also do an instance segmentation that says, I want to differentiate between person 1, person 2, car 1 and car 2. So in this particular slide, what you're seeing is there is pretzel, but there are 3 different kinds of pretzels, like one is Flips, Hershey's, and Keys. So that is instance segmentation. So try to get an idea of what semantic segmentation is versus what is an instance segmentation is. I also want to point out that there are many terms that could be slightly different from each other. For instance, classification versus object recognition versus object detection, object segmentation, instance segmentation, and let's say semantic segmentation. So I would encourage you to kind of look into these terms so you understand the differences between them. Sometimes object detection and object recognition are kind of used interchangeably. But I think they have subtle difference from each other. For instance, detection is more about localization in the image space or 3D space, depending on the input data. Whereas recognition is like you are given something and you're asked to recognize that. So it kind of falls into the category of classification. So be mindful about these terms, and I would highly encourage you to kind of look up and see like formal definitions of these terms. Okay, so one thing to note is most of these other tasks have been kind of built on top of what we call the foundational block, which is image classification. Before we talk about object detection, I kind of missed out on the lectures in the training neural networks 2, where we are talking about transfer learning. So I want to like bring that up here so you can understand how the image classification has been used as a building block for these other computer vision tasks. Okay, so transfer learning, which is a very common term that you will hear, especially in deep learning, irrespective of the domain. This is basically referring to what we call as generalizing to new set of tasks. So in the context of CNNs, what we call as transfer learning is, let's say we train the entire network on the ImageNet dataset. And what you can do is you can remove the final layer, the last layer, which is converting the 4096 into 1000 values, especially if this is trained on ImageNet, we have 1000 classes. So that's what the first figure is talking about. The second figure, you're like, okay, I'm going to stop at the place where there's feature extraction is done, but I'm going to add a final layer that would help me do a different task on a different data set. So for instance, let's say we are freezing all of these weights up to the last layer, and you have removed the layer and you have changed that fully connected layer to something else. For instance, if you want to do, let's say, classification on Caltech, or classification on your props dataset. So then you want to convert the 4096 into the labels that is corresponding to that particular dataset. So again, we are, let's say, like we are doing image classification, but transferring from one dataset to the other dataset. So there are works that basically have benchmarked and talked about like the aspect of feature extraction using CNNs. So if you think about the lectures that we that was on deep learning, like so I talked about how image classification was done before the deep learning era and after the deep learning. So in the before deep learning, you had this two stages where you had a feature extraction followed by a linear classifier. And then when deep learning came into picture, we were like, let's do it end to end. So here we are going back to the first phase where you are like, we're going to use the CNN to give us features, and then we are going to train, let's say, an SVM or logistic regression to actually do the classification on this new data set. So we are not updating the weights on the entire network, which mostly is called as backbone. So what you're seeing on the right side is classification accuracy on a Caltech data set, especially if you're looking at the green graph plotted here. What is happening is you're using the feature extraction, and then you have an SVM layer that does the classification for you. So you can see that by exploiting this frozen network, which was trained on ImageNet, which is the backbone here, you can actually get much better classification accuracy as opposed to not using that, let's say using Yang et al. Work, which is plotted in the red color here. So this has been shown on multiple datasets. For instance, bird classification in this different dataset called Caltech UCSD. So until at this point, you see 56.78 has been the accuracy before we start using AlexNet plus logistic regression. And if you use AlexNet plus their own method, which did not have this backbone, you see a boost in the performance. So in the same paper, there are a bunch of analysis that talks about like how this idea of using CNNs for feature extraction followed by a classification gives you better accuracy. This has also been shown on many other data sets and many other tasks. For instance, here, so before prior to the state of the art, the plots that you see for object classification, scene classification, birds, flowers, human attributes, and stuff, you see the blue bar is the accuracies. And then the idea of using CNNs for your feature extraction followed by SVM, or you have some sort of augmentation techniques followed by SVM, you can see that there's a boost in the performance. So this is one way of doing transfer learning, where you're using CNN as a feature extractor, which means you are not changing the weights, but you're only training on the last layer for the new task. Is that clear? Any questions so far? Okay. So this was a feature extraction. The other thing that you can do is what we call as fine tuning. So in this particular case, you will add the new fully connected layer, but then you would continue to train the entire model on the new task. And of course, there are like tricks to do this. You don't have to do it for the entire model. You can do it on a partial model. You can also have some kind of training schedule so that it works out and doesn't go like crazy in terms when you do optimization. So some of the notable tricks here is that are basically you train with the feature extraction first before you fine tune the entire backbone. For instance, you start training your fully connected layer before you start to do the backpropagation to the entire model. The other trick is you want to lower your learning rate than that was used in your original training, because you don't want your weights to change by a large amount for the backbone. Sometimes it's also useful to freeze your lower layers. That is because your lower layers, which are like more close to your input, are extracting these representations that are more fundamental. Like, for instance, they could be capturing information like edges, corners, and then trying to find color gradients and so forth. So maybe it is okay to save those layers or freeze those layers so that you can save on computation. And especially like we talked about earlier, backpropagation is computationally expensive. So the more time you save on that, better for you in terms of training. Okay, is that clear? Like, what is the difference between the feature extraction followed by linear classification versus fine tuning in this particular slide? So compared to feature extraction, fine tuning requires more data, meaning you're backpropagating for like larger network as opposed to just your fully connected layer. So it's computationally expensive, but we have seen that it can give you higher accuracies as opposed to just using CNN as a feature extractor. So during that time, I think it's become evident like to do transfer learning. And especially the trend is any architecture that performs really well on ImageNet classification tends to be good at transfer learning. So people would watch out for these recent advancements that are happening in image classification challenge or ImageNet classification challenge, and then try to use the same architecture and then do fine tuning for any other tasks. For instance, it could be a medical imaging application, or it could be like for robot perception and so forth. So there's also this work that kind of compared all of these architectures on COCO dataset, specifically for object detection task. So please note that object detection is not what ImageNet was trained for, right? But then this particular work talks about, okay, there is a generalized framework that we can do for object detection, where you have backbones that are coming from ImageNet classification task. So before deep learning, deformable parts model like gave around like, let's say 5% accuracy on doing detection on COCO. By using fast RCNN, the framework that they proposed, which uses AlexNet, you get a bump of 10% in accuracy. And when we start using a better backbone, which is VGG16, you get much more accuracy or performance. And then then came the newer architecture, which is faster RCNN. So which means it is a different framework for doing object detection, but it uses VGG16 as its backbone. So again, when you start using ResNet 50 instead of VGG16, with the faster RCNN framework, you had a higher accuracy. And this particular trend continues from then on. So I think the more recent one is mask RCNN, which is prominently used for detection and segmentation. And as you can see, it kind of capitalizes on the fact of the better architecture that performed better on ImageNet classification. Okay, so what are the things to consider for transfer learning in convolutional neural networks? So one nice way to look at it is how similar is your data with respect to the ImageNet or the data that is being trained upon, and what is the data that you have for this new particular task or new data set that you want to work on. So for instance, let's say you have less data, but the data is more similar, or the distribution is almost similar to what you will see in ImageNet. Then it is recommended that you just have one particular classification layer and not do what we called as fine tuning. You can just use feature extraction from the ImageNet trained architecture, and then have one particular classification layer to perform the task. If you have lots of data, which means you want more accuracy, what you could do is you could train the other layers as well. So you can try to increase the number of layers that you want to train and get from more specific to more generic layers. Now, let's say your data is, you have large amounts of data, but your data is different from what we see in ImageNet classification or ImageNet dataset. For instance, let's say it is on 3D imaging or medical imaging kind of task. Then I think it is better to fine tune a large number of layers. That is, you actually almost look into the lower layers as well in your fine tuning process. But now let's say your data set is completely different from ImageNet, but you only have less amount of data, which is quite common in medical domain. Then I think it becomes a little harder to figure out, like, okay, you might want to think about having a linear classifier at different stages. So that could give you signals of what to use and what not to use. In other words, like it's a difficult zone, and there's no I want to say fixed way of looking at this problem. You might want to try many different things to make it work. Okay, so at this point, you should also be thinking like, okay, what if I used the entire data set, but did not have the pre-trained weights. It happens that you can still get good performance, but then you will have to be training for a longer period of time. So this is one analysis that was done in 2019 in this particular paper, where they talk about, okay, I'm going to initialize with the pre-trained weights, and I'm also having another model which is randomly initialized. So from this plot, what you can see is if you're initializing with the pre-trained weights, you converge faster as opposed to doing it with random initialization. But you can still get closer to that accuracy if you train for a longer period of time. So which means your entire network is basically trained on your new task, and you're not making use of the fact that pre-trained models are already available for you to use. Okay, any questions so far? It's hard to see people, so if you have any questions, please unmute yourself and ask. Okay, so transfer learning is very pervasive, and it's commonly used these days. For instance, we recently saw this announcement that there is a workshop that talks about pre-training for robotics. So this is a very active area of research, and so this conference is happening in London in May. It's a full-day workshop, and I hope they will do recording. And not only this, like the most recent conferences in robotics has this idea of, or has a workshop of pre-training for robot learning. So if you notice the important dates, and if people are interested in doing research further and maybe going to grad school, if that is of interest, they have a submission deadline, which is April 14th. And if you are picking this particular topic, or if you are leaning towards this, it's probably a good submission to make. Okay, so now let's look at how we can do transfer learning from image classification task to other tasks, such as object detection. So let us define object detection first. So the input is an RGB image, and the output is a set of detected objects. And for each object, you have a label. So there's a category label as the output, and the corresponding bounding box that kind of says where this particular object is. So it's basically 4 numbers, which talks about the XY pixel for the left top corner of the bounding box, and the width and height that decides the width and height of the bounding box. A few challenges in object detection. One is you have multiple outputs. So it's not like image classification. So image classification takes one image and gives you one label. But here, that image might have a variable number of objects. So your network or the architecture has to be kind of flexible to be able to, output multiple outputs. And also like multiple types of outputs. So we are looking at not only one output for every detection. We are talking about what is the detected object and where is it actually in the image. So there are multiple outputs for each, multiple types for each output. And the last one is the object detection should work irrespective of the bounding box size, meaning your classification works for, let's say, one particular dimension, which is 224, 224. It doesn't matter if the image has a different resolution, you still should be able to use that block for doing your detection. So these are some of the challenges. And let's also kind of think about the bounding box. So bounding box are typically axis aligned. So when I say axis aligned, you can imagine it's basically rectangles where the axis is aligned to the X and the Y axis of your input image. Oriented boxes it's less common, but as depicted on the image, so it's not axis aligned, it can be on any orientation. You will see this less commonly in the literature. The reason behind that is it's actually really hard to annotate or get ground truth labels. So imagine, right, if I give an image and ask you to like annotate objects in the image, it's easier to click and drag and give me a bounding box than having this additional stroke of saying, okay, this is the orientation of this object. So in other words, if you really care about tightly bounded bounding boxes, one way to think about is if the task has to be segmentation, more so than detection. Okay, so the other type of bounding boxes that you'll probably see, which alludes to what we call as a model detection, is when your bounding box covers the entire extent of the object in the space, even though only a few pixels are corresponding to that particular object in this particular scene. So for instance, the blue bounding box is probably what we call as modal bounding box. So it limits itself to the pixels that is corresponding to that particular object, in this case, flips. Whereas a model detection is basically when your bounding box is trying to cover the possible portion of this object in your image if there is no occlusion by other objects. So if you had paid attention to the video earlier in the slides today, especially showing how detections are happening on the props dataset. So that was using the ground truth detections. And you could have seen that it had a model detection, like the bounding boxes were covering the object, even though only a few pixels of the object were visible from a particular viewpoint. Okay, so how do we compare different bounding boxes, especially between the prediction and the ground truth? So comparing bounding boxes. So the metric that we will use is intersection over union. For instance, let's say the green box here is a ground truth for the pretzels. And the prediction from a neural network or a learning model is the one that is in the cyan color, or the other green color that you see here as our prediction. So the intersection over union is basically area of intersection divided by the union. So the area of intersection between these two bounding boxes divided by the union of these two bounding boxes. IOU is also called Jaccard similarity or Jaccard index. So if you're reading a paper and it says Jaccard similarity, it's basically intersection over union. Okay, what is a good number for IOU? So let's say your IOU is greater than 0.5, then I think your model is doing pretty decent job. If it is, let's say, above 0.7, I think it's doing a pretty good job. And if it is like 0.9, it's almost perfect and trying to give similar output as compared to your ground truth. Any questions so far? Okay. So let's say we want to do detection for one single object, meaning your image always has one single object and you're trying to detect. So one simple extension that we could do from image classification architectures is we will take out the fully connected layer at the end and then train a new classifier by using the features from your pre-trained ImageNet-based neural network. And then that can give you the new classes. So this is what we saw earlier, like in terms of transfer learning using CNN as a feature extractor. So you just train on the new linear classifier, which classifies which particular object this is. You can also use the same feature and train a regressor that will regress you the bounding box coordinates, which is in XY width and height of the bounding box in your image. So as we saw earlier, softmax loss is good enough to do linear classification, especially classifying it to one of these labels. Whereas L2 loss is probably preferred when you're trying to regress bounding boxes. So the top portion, which is on classification or more of recognizing the object, is talking about what is in the scene, whereas the bounding box is talking about where this object is in the scene. So you could do weighted sum of these two losses, softmax and L2 loss, and which is what is sometimes referred to as multitask loss. And you can have a hyperparameter for lambda that kind of figures out how much weight you want to give to each of these laws for learning together. The reason behind using this gamma is these two losses are completely different from each other. Like they kind of explains two different things. So you don't want one to overpower the other. So by looking at the values that you have for softmax loss and L2 loss, you can come up with this lambda that kind of considers both of these laws in the same grounds. Okay, so as we saw earlier, this could be considered as doing transfer learning. So if you think about it, you can do this using transfer learning of the type feature extraction followed by linear classification, or you can also do it like fine-tuning where you are trying to use your data set for fine-tuning the entire network. So the problem that we are not addressing at this point is an image can have more than one object. So this works if you have single object. So you can get a classification, you can also get a bounding box that kind of says where the object is. But what if your image has more than one object, which is often the case, right? For instance, the running example that we have for this class is you might have multiple objects in the scene and you want to be able to have a robot perception algorithm that kind of gives you information about all the objects in the scene. So it could be that you have many objects in your environment and you want to be able to detect all of them. So one simple way of doing this is using sliding window. So you take all possible bounding boxes in your image, and then for each of this bounding box, you let it run, or the cropped image, you let it run through an image classification framework or network that gives you the classification of that particular patch or the crop. So in this case, so it's the top left corner, and it's basically the background. It is not talking about any objects of interest. But let's say there is a bounding box of this kind, which nicely overlaps with this particular object, then your image classification network should be able to classify them. Similarly, if you're moving the box to a different location, you might be able to classify this particular bounding box as well. The problem here is that you have so many possible bounding boxes, right? If you consider an image of size H and W, the number of possible positions in X direction and Y direction is, as noted on the slide. So it's W minus small w plus 1. And the number of possible positions in the image is a product of W minus small w plus 1 multiplied by H minus small h plus 1. So these are only the positions, right? Like if you think about the possible bounding boxes, they're much higher. So one example is if you have 800 cross 600 image, you might end up with like 58 million bounding boxes, and there is no way we can evaluate all of them. And you don't want to do that too, right? You want to have more smarter way of like thinking about these bounding boxes. So one way people have handled this is by using this module called region proposal. Here is basically you use a set of heuristics to kind of give you a bunch of bounding boxes in the image and say, okay, these are the objects in the image, or these are the bounding boxes where there is something called object. So there is an objectness in the image or in that particular portion, and let us try to classify that particular portion alone. So generally, this is like small set of bounding boxes, and we want to have heuristics such that they can cover all possible objects in the scene. And some of the heuristics are like, okay, is it looking like a blob in the entire scene? Relatively faster heuristics are basically what we call as selective search. So one idea here is before deep learning came into picture, people were still doing object detection. They were using heuristics to do this. So they were coming up with these heuristics similar to what we did for image classification, saying, okay, there is an edge, there is a corner. Maybe we should group them together and say, call that as an object. And then say, okay, this is the crop that we care about. And we want to classify what is in that particular crop. The trend in the community is when there is something working on heuristics, there's more likely to cause friction, meaning there is a lot of input from the user or the practitioner. So you might as well be able to learn that using data. And so far, we have seen that particular trend is proving to be correct. So when you have enough data, we can come up with this region proposals as well. Okay, so that leads to a popular framework, which is RCNN, which refers to region-based CNN. So what RCNN is doing is, let's say we have some heuristics for this particular input image, and you have a bunch of bounding boxes that was proposed. So each of these image is warped into an image that is of size 224 cross 224. So irrespective of the size of the bounding box, all of these patches are converted into this standard size. So this goes into a neural network that does classification and also regression. The thing to note here is the bounding box regression here is basically predicting a transformation so that it can correct the numbers, the 4 numbers that was used for warping that region. So let us dig into this in more detail. For instance, let's say you have a region proposal with center px and py, which has pw and ph. So this is the region that was proposed for doing classification. And let's say you have a model that kind of predicts tx, ty, tw, th after the regression task. So this transform is basically trying to resize your region proposal so that it matches well with your expected ground truth. So what's happening here is you're trying to transform your px, py, pw, ph into bx, by, bw, bh, which is the output predictor output that you want to predict for the entire image. And the way you're doing it is you're trying to shift the center using this tx and ty, and you're scaling your pw, ph with tw, th. So please pay attention to the slide so you can understand the elements that I'm talking about. So you have a region proposal which has px, py, pw, ph as the input to your regressor. And then the regressor outputs or predicts tx, ty, tw, th. The idea behind this is the tx, ty, tw, th should be able to adjust your px, py, pw, ph into the output bounding box that you are expecting. So if you think about it, if the tx, ty, tw, th, if all of them are zeros, basically you're not updating your region proposal. you're leaving it as such. You're like, the region proposal is good enough. I'm just going to classify that region to be, one of the labels. So an L2 regularization that you can add can actually encourage leaving the proposal to be unchanged during the training process. And the bounding box regression is basically scale and translation invariance, meaning the difference between the proposal and output is kind of handled by this transformation that you have as intermediate output. So in other words, the CNN does not see the absolute size and the position of your proposal. So if you want to think about it from the training point of view, let's say BX, BY, BW, BH are coming from your ground truth. The way you can compute TX, TY, TW, TH is just by inverting the algebraic operations. Is this clear, like how RCNN is doing? I think the thing to remember is this particular left slide. So you take an input image and you have region proposals. Let's say the region proposals are coming using some heuristics. You watt the images, it goes through convolutional neural networks. Again, these convolutional networks can share the same weights. So you can output a particular class and a bounding box.
I have a doubt about this.
Yeah.
So you're giving like, let's say 2,000 regions of interest, but you only need like 5 of them. So like for the others, do you classify them as being like not being the target? Like how is it?
That's a good question. So the next few slides will actually answer that.
Okay.
So now we talked about like how you're not like kind of pruning the proposals. Let's say if you're giving 2,000 proposals, the output so far that we discussed is that it's going to have 2,000 proposals, meaning you'll have 2,000 labels and 2,000 bounding boxes or transformed bounding boxes. So for instance, in the training, you have ground truth and you have region proposals. But then what will happen to these proposals is that they're going to be categorized into positive, negative, and neutral. We'll see how to do that. So for instance, let's say we are only looking at classification as a problem. So you're categorizing them into positive, negative, and neutral based on the labels. But you can also use how they're overlapping with the ground truth boxes to kind of ignore them, right? For instance, you can say that it is positive only if it has 0.5, IOU more than 0.5 with respect to the ground truth bounding box. If it has an IOU of less than 0.3, you can say that that is it's a negative region, and you can have a neutral region that is between 0.3 and 0.5. So the way you can do this is you will have these bounding boxes going through your image classifier and also regressor. So which kind of gives you the target and also the bounding box. During the test time, what can happen is you will get the class scores and also the transforms. And of course, you can use the thresholds to get a set of detections. You can have the IOU help you figure out if that particular region proposal is useful or not. But then you also have this problem of outputs having overlapping bounding boxes. And you probably also need to figure out how to set this threshold on your IOU. So let's take an example so it's very clear. So let's say we have this overlapping bounding boxes. Like again, like as the question was asked, let's say we have so many bounding boxes, so we might end up having overlapping outputs. So in that case, the solution is basically you select the highest scoring bounding box, eliminate a lower scoring bounding box, which has an IOU that is more than 0.7 with respect to the first selected bounding box. And you repeat this if you have many bounding boxes left. So for instance, if you take an example here, so the highlighted in pink color, so the pretzels, which has a score of 0.9 from the classification. If you take that particular bounding box and compare with the other bounding boxes and compute the IOU, so you can see that it's overlapping much more with the bounding box that is also in pink in color with 0.8 as a value. Whereas with the other blue bounding boxes, it has very small value in terms of IOU. So now you will basically remove or eliminate the bounding box that you saw earlier. And now you will repeat the process for the other bounding boxes that are left. So you can remove the other bounding box on the pretzel as well. Is that clear? So this technique is called non-maxima suppression, and it's very, very well-known technique, and it's been there for like many years now. Before even like neural networks came into picture, people have been using this for a while. Okay, so but the thing is, this non-maxima suppression may also eliminate good bounding boxes if your scene is highly cluttered, meaning it's highly likely that you will see so many overlapping bounding boxes. There is no good solution, and I think it depends on the application as well. So at some point, if you may have to move to segmentation, instant segmentation, if you're caring about more accurate precision in the space of the image for figuring out where the object is. Does that answer the question that came earlier?
Yes.
Thank you.
I had a quick question. So you came up with the region proposals, but like even for training part, we already assumed that we had some kind of region proposal. Like how do they come up, or what heuristics? How do we come up with those heuristics?
Oh, so the heuristics are like, for instance, you can refer to RCNN to see what they have done, but the other heuristics are basically image processing techniques. So you will try to come up with heuristic that says, okay, if there are these groupings of edges or patches of colors, I'm going to say that that blob will give me one particular bounding box. So you basically draw a bounding box around a particular blob and say, okay, that seems like an object. Let me classify that.
Okay.
But there are also like region proposal networks, which are trained to give you bounding boxes. So for those networks, the input is basically an image and the output is bounding boxes. So they are only trained to give bounding boxes of what looks like an object. So they're not doing any classification. They're trying to just draw a bounding box, and that there are networks that does that as well. So they are called region proposal networks.
Okay.
Okay, so we saw non-maxima suppression that eliminates multiple overlapping bounding boxes. Now let us look at how to evaluate object detectors. So let's say you have trained the RCNN, and now you're looking at a bunch of test images, which goes through the network. And then you did this post-processing where you kind of use non-maxima suppression, and now you have a bunch of outputs. So you would actually try to do what we call average precision for each category. Average precision is defined as what is the area under precision recall curve. So let us go through this example so you kind of understand what that is. So in all of these test images, we care about only pretzel. So first of all, let's do detection for pretzel in all of these test images. And we will rank these detections from high score to low score. So as you see in the right side of the slide, there are five number of detections in all of the test images. And for each of the detection, there is a ground truth set of detections on these test images as well. So now you will start from the highest scored detection and see which of the ground truth bonding box has a match that is over 0.5. If it is matches very well, you will say that that is the positive. So then you will plot that on your precision recall curve. So precision is how precise your detection is with respect to the ground truth. So the first ground truth, it matches pretty well. So your precision is 1. Whereas recall is looking at all possible ground truth pretzel bonding boxes that you have. So there are 3 bonding boxes that you want your model to recover, but so far we are only at the first step. So it's 1 out of 3 at this point. So the recall is 0.33, whereas your precision for this particular instant is perfect. Now let's move on to the second detection for the pretzel. And this one matches with the other ground truth as well, with an IOU of greater than 0.5. So again, at this point, we are 2 out of 2. Whereas we are still progressing in terms of figuring out whether the recall is good enough. So at this point, the recall is 2 over 3. Now you're looking at this, the third detection, and in this particular case, let's say it is not having a match with the left out ground truth, which means it is possibly false positive. Right, so which means you are saying that the precision at this point is going to reduce because the third one did not match with the ground truth. And the recall at this point is also 2 out of 3. You still have 1 ground truth to recover. The same thing goes for the next sample as well. So you're still not able to match that with the ground truth with an IOU. So your precision is still 2 out of 4. So your model is able to predict the first 2 detections to be perfect, whereas the second 2 are wrong. So your recall is still 2 out of 3 because recall always uses the number of ground truth bounding boxes. For the last one, let's say it matches with the ground truth. So then your recall jumps to 1. And so far, the precision has been 3 out of 5. Does it make sense? Like how we are calculating the precision and recall and how we are plotting, starting from the highest score detection to the lowest score detection. So now if you plot, you can actually capture the area under the curve. And that is the average precision for this particular category, which is pretzel.
Prof, I just have one question. So the scores over here, the probability scores or the IOU scores?
So the scores that you see 0.99, 0.95, they are probability scores.
Okay, the model probability scores. Right?
Yes. Yeah.
Okay. Yeah.
That question leads to a good follow-up question is, so we fixed this IOU threshold to be 0.5, right? Only then we were able to see how well it matches with the ground truth.
Right.
So this particular average precision is conditioned upon this threshold that you chose, which is 0.5.
Correct.
So you can get different average precisions for every IOU threshold that you choose.
Got it. And you take a mean across that, so that's the mean average precision?
Yeah, so if you take a mean across all the categories for a particular threshold, that becomes your mean average precision.
Okay.
So which is
Right.
also indicated more commonly as MAP at, let's say, 0.5. 0.5 is the threshold that you chose. So depending on the, so the thresholding is a choice that people would use when you're doing, let's say, inference or the testing. When you, let's say, it even goes into the production line, you want to figure out what threshold is good for having a good performance. Okay, so we calculate average position for every category in your data set. And then we average that over all the categories, which gives you the mean average position.
I have a small doubt. So basically, we are comparing it with the ground truth twice, right? Once during NMS, like non-maximum suppression, you use that to eliminate the other boxes. And then again, you compare it with the ground truth for the precision and recall, right?
Oh, okay, that's a good question. So maybe it was a little confusing. So for non-maximum suppression, you are not using the ground truth. So these are 4 detections that you got.
Okay.
But then you are like, okay, they are overlapping with each other. So maybe one of these 2 or like 2 of these 4 is correct. So how do you eliminate the other bounding boxes? So the way to do that is you will take, start from the highest scoring bounding box, and then pick the bounding box that has a IOU threshold of greater than 0.7 with the selected bounding box, and then see if there is too much of overlap, you kind of eliminate that.
Okay, got it.
Yeah, so non-maximum suppression is post-processing. It does not use the ground truth.
Okay, thank you.
Of course. Okay, so yeah, that ends today's lecture. So we'll continue on object detection in the next lecture, and we'll also talk about segmentation a little bit. So with that, I will end today's lecture.